Again, we're going to start with an example. This example for the things we've just discussed in the part 1 of the lecture before the break. So we have the following situation. This is a fuel tank for a car, and the fuel gauge actually reads a pressure and indicates on your car instruments the level of fuel according to the pressure. It's sort of calibrated to convert that pressure to a reading there in your needle that says full, empty, 1/4, etc. So the tank is 30 centimeters deep, but in this case it accidentally contains 2 centimeters of water at the bottom. Of course, the water goes to the bottom because gasoline is lighter, plus gasoline at the top. So the question is, how many, should say many, centimeters of air remain at the top when the gauge erroneously reads full? So we have here a situation of pressure readings according to different heights of gases. You're told that there's 2 centimeters of water at the bottom, there's an unknown layer of air at the top, and the whole tank is 30 centimeters, and the gauge reads full. So, what's our solution? If the tank were full of gasoline first, what would be the pressure? We would have 30 centimeters of, that would be the column of gas, right? The whole tank full of gas. So the pressure at the gauge for a full tank is equal to the specific weight of gas multiplied by h, well, the full height of the tank, which is given. So we can calculate this. We're given the specific gravity of gasoline, so we can use specific gravity of gasoline and multiply by the specific weight of water. And we're going to probably need to choose a density, because you go to a table on your book and you will have the specific weight or the density of water for different temperatures. You can choose 20, 25, something reasonable. And just as long as you put it there on your solution, what temperature you've chosen to solve your problem, all is fine. I have chosen 25, which is not actually standard. Perhaps 20 would be standard, but this is what I decided to use when I was solving the problem. And so I have 0.68, the specific gravity, multiplied by the density of water, 997 kilograms per cubic meter, the density of water, and the acceleration of gravity. So this would be rho g of water multiplied by the specific gravity gives me gamma of the gas, meters per square. So this is rho, and this is g. And the complete height of the tank is 0.3 meters. I've made my conversion immediately because going from centimeters to meters is quite easy. I don't need to use the grid method here. I can already do it in my head. Yes? Full with gas. For a tank full with gas. First of all, to just see what would be the reading for a tank full of gas. Because the problem says that it erroneously reads full. So what I need to do is find in the situation of water, gas, and air, what is the distribution of how thick those layers need to be to give me the same pressure as if the tank were full of gas, because the gauge reads full, and I think it's only gas, so that's what it's indicating to me. Yes? because we're multiplying by the specific gravity here. So the specific gravity is gamma of the gas divided by gamma of water. And so by multiplying by gamma of water, I get gamma of gas. So this is something important for you to learn how to use specific gravity in calculations like this. It's very useful because basically over time you kind of memorize the density of water for a certain, for a condition which is obvious, or you use that table all the time, so you have your table for the density of water at 20 degrees or 25 degrees, and you're very quick with getting numbers out of it because you use it all the time. And then all you need is this extra little number that gives you the relative weight between a material and and water. And that also you sort of learn, some of these values you can memorize just by using them. You don't try to memorize these numbers. You use them several times and they just become second nature, like gravity, say 9.8, meters per second square. It's just those numbers, you use them a lot. So this is what we've done here, and I multiply by this. So this is just basically gamma H. It's just that I've taken a few steps to get to gamma H. Okay, so we have all of that. All of it is given, which means I can have the pressure, which is the pressure that produces a reading of full. I calculated this, and it is equal to, according to the numbers I have here, 1993 Pascal. This vent here indicates that this is, of course, connected to the atmosphere, so this is gauge pressure. So always think to yourself whether the pressure that you're talking about is absolute or relative to atmosphere. Take a moment to make sure that you understand what you're calculating. Yes? You could by adding the atmospheric pressure. But do we need to? We don't need to in this problem. But when would we need to? If we were to use any thermodynamic relation, we would need absolute, right? Ideal gas, then we need absolute. Here we don't, because we're just going to compare two different pressures. Get absolute, because this is relative. Gauge means it's relative with respect to atmosphere, and you need to add atmospheric pressure to get absolute. The standard atmospheric pressure, the pressure of 1 atmosphere at 20 degrees at sea level, is also value that you get from a table. So now this is the pressure that we need to set equal to, well, the situation that we see in the picture. 2 centimeters of water plus some distance of gas that we don't know, X centimeters of gas. This is our unknown. But the gauge reads full, so it needs to be the same pressure. You agree? Everybody happy with that? Good. Okay, so we set it equal to 1993 pascals is equal to, okay, water 2 centimeters, so I'm going to convert to meters right away, 0.02 meters. And we have gamma of water, so this is rho g of water. I can put the number right here, 9780. This, by the way, is at 25 degrees Celsius from a table, Newton cubic meter, plus a certain weight of gasoline that we don't know. So again, we have the specific gravity, 0.68 times 9,780 gamma of water, newtons meter cube, and the distance, x. We don't know, but x in meters, right? But x is our only unknown in this equation. So basically we can solve for x very easily here. Take this number, subtract this, and divide by that, and we have x. You can put the numbers immediately in the calculator now to get x. Right? Good. So x, if I haven't made a mistake, is 0.27 meters. That's the height of gasoline. Are we done? Very good. Why not? We're looking for the height of air. Very good. Very attentive students here at the front. And this is the type of thing that can kind of get you in an exam if you didn't read the question carefully. You need to kind of have your full focus in reading the question. You think you're done, go back and actually check what am I being asked. You're being asked for the air at the top. So to get the gap of air, at the top, we need to take the full height of the tank, which is 30 centimeters, minus the 2 centimeters of water at the bottom, and minus what we just found, which is the height of gas. And we get 1 centimeter. And that is our answer. Another example. So this case has a tank of water and a mercury manometer. And the question that you're being asked is to find the ratio between HW over HM. In case you can't see very well in my picture, this is HW and this is HM, and this again is HM. So these two guys are equal. They're both HM, and this is HW. And you're asked for the ratio HM to HW. So what do we know? Well, we can start our process of typical process for a manometer problem. This is going to be a row of water, and we start by going to say, let's call this point over here in the interface, let's call this one point 1. For some strange reason, I called this one my solution number 2 and this one number 3. And so let's be consistent with that so I don't make a mistake. Point 1 and point 3, the way that I've drawn them, are 2 points in the same fluid at the same elevation, and so they have the same pressure. So immediately I can write P1 is equal to P3 from the picture. 2 points in the same fluid at the same elevation. And I'm going to call the gamma of mercury gamma M, for water gamma W, and so we have P1 equals P3. So, yes, a question. HW, which is this guy over here, is the height between the surface of the water in the tank and this point in here. So this point up here is atmospheric pressure. The pressure at that point is atmospheric. So that question immediately leads me to write down what the pressure at point 1 is, because I can see that point 1 is all of this column of water up to here, plus this little extra column here at 1. P1 is, we have water all the way, so gamma of water. But the total height is this HW plus this little extra bit here, which is HM. That is the pressure at 1. Everybody clear with that and happy with that? Okay, good. At 3, well, you see at 3, if I look for it from the other end, here I also have atmospheric pressure applied in all the way to this surface. This is open. There's a vent here. It's open to the atmosphere. So at 3, I have just this column of mercury from 2 to 3, right? From point 2 to point 3, which is gamma of mercury. And the distance I have HM plus HM, 2HM from the drawing. And these two must be equal to each other. P1 equal to P3. So now I can write HW times, gamma W, HW plus HM equals 2 gamma M HM so I'm going to collect together the terms that have HM on the right hand side, and I will write gamma W HW is equal to, and I have HM multiplied by this that I brought from this side and this over here. So 2 gamma M minus the one that I brought from the other side, which is gamma W, water. And now I can divide both sides of the equation by HM to get the ratio that I'm being asked for. And I can divide over by gamma to the other side to clean it up. So HW divided by HM is 2 gamma M minus gamma W divided by gamma W. Or I could write it as 2 the specific gravity of mercury minus 1. And I actually can look up the value of the specific gravity of mercury and solve this from a table. I can get the value of specific gravity of mercury is 13.56, and I can put this back in the equation and get that HW divided by HM is equal to 2 times 13.56 minus 1, which is equal to 26, about 26.1. This has no units because it's a relative, two lengths, so there's no units, and this is our result. So the trick of this whole gamut of problems with manometers is to look always at 2 points which have the same fluid at the same height. And that's going to be the key to write down an equation, as you can see here. P1 equals P3. And then I can follow the columns of liquid and build my equation on the basis of this observation. Yes? Sorry, can you repeat? I couldn't hear you. Atmospheric pressure is acting on both sides equally, and basically I could include it, but it would just make my life a little bit harder because I would have to keep track of it on all of, it's acting everywhere equally. So I could just work, that's why we work with gauge pressure, because it makes it a little bit just easier for the bookkeeping. I don't have to keep track of the atmospheric pressure. It's acting everywhere. Yes? No, it's not necessarily. It doesn't look like it's the height of the tank. It's just a height, and they, the sort of the height to the mid-level of this column of mercury here. And so they've measured HM up and HM down. So it's just the midpoint of this column. Doesn't have anything to do with the height of the tank. Good? Are we good? Okay. So to finish this section on manometers, which are instruments to measure pressure, I just want to point out that there's some other instruments available today. Manometers are still used to this day quite extensively, but they're a very traditional instrument from quite sort of, you can find antique ones even. But today we have available other sorts of devices to measure pressure. So I just want to point out that there's some mechanical and electronic devices that we can use. One of them is called the Bourdon pressure gauge. Remember that also manometers, if we're looking for columns, if we're using columns of liquids, it's kind of limited the range of pressures that we can measure with a column of liquid. So if we have really high pressures, it's going to be difficult to use a YouTube manometer set. So pressures that are not too far from atmospheric, we're okay. But if we have complicated system with very high pressures, or if we have pressures that change in time and we want to record that, we need an electronic device of some sort. So there's some modern devices that we can use for those applications. So this one is a Bourdon pressure gauge, which uses a mechanical element. The mechanical element is shown on this picture over here. What this is really like a hollow, curved tube, okay, of metal. This hollow curved tube has is connected on one side to the pressure that is being measured. So if we look at, say, here, this tube will be connected to the pressure that is being measured. This pressure comes inside the tube, and you can imagine that if we put more pressure, it's like these sort of these old birthday things that you blow, that are like this, and you blow in there, and they straighten up. Those old, yeah, you remember that? Okay, the same idea. You blow on this, you apply a pressure on this curved element, and it sort of wants to straighten out a little bit. It's a metallic element, it's hollow, and it's, it's elastic because the metallic material is elastic. And that small change in the shape of that curved element is read on a needle and calibrated to indicate the pressure changes. Okay? So you have to calibrate this thing here. Now the one interesting thing is that, so the motion of this tube, the motion of this metallic element is translated into a reading of pressure as the tube tends to straighten, like a birthday little, how do you call those things? Who knows? Yeah. But you know what I mean. What do you think would be the pressure when this reads 0? Atmospheric, very good. Equals to atmospheric. So one thing that you can notice here is that we have numbers on two sides of 0, because the same as we can blow in this little tube, we can also sort of, apply a negative pressure basically. So this reads both negative and positive pressures around the atmospheric value. So positive and negative with respect, so this is gauge pressure, right? You can have negative gauge pressure. Of course, if it's absolute pressure, there's no negative, right? Pressure is always a positive. Absolute pressure is always positive. But gauge pressure can be negative. We can have a sort of small suction pressure, a small value below atmospheric. And this guy can read both positive and negative values. Okay, this is one. Then this is very standard. You see them all over the place if you go to sort of process plants or chemical engineering installations. This is a very standard instrument. This other one is called the aneroid barometer. It's also a very classic device. And again, we have a metallic element, which is this hollow little, in this cartoon, there's a cut through what is really like a pillow, like a little pillow of metal. This little pillow of metal is actually hollow and evacuated. They've actually sucked out all the air from it, so it's at a vacuum inside, pretty close to vacuum anyway. And so this elastic element will change will also deform responding to outside pressures. And that deformation, that motion of that little element is read by some sort of mechanical lever which turns a needle. Simple as that. And the changes on the pressure deform this little pillow and are read in a needle. So what pressure are we measuring here? We're measuring actual atmospheric pressure for this guy. So this is used to, that's why it's called barometer. It measures atmospheric pressure. Okay? The changes in atmospheric pressure deform the cell. And these changes are, this deformation is read into, this is read into a little needle indication. Now, this also has a very, very important use for those of you who are interested, or perhaps doing your aerospace concentration, interested in airplanes. This is actually the mechanism by which the traditional airplane altimeters are based. An airplane altimeter, which kind of looks like that, the instrument on your panel will look similar to what is being shown in this picture, very similar, but really what you have behind it is an aneroid barometer. The only difference is that the needle is calibrated to tell you not the pressure, but the height in the atmosphere that corresponds to that pressure for a standard atmosphere. So also you may notice that there's a little, perhaps, yeah, you can see that there's sort of a little extra numbers in there. What you have is normally you would have a little, you will have a little wheel here or something that the pilot can manually change, and you change it to account for variations in pressure in the airport. So the guy at the tower will tell you when you're approaching, the reading, you set your altimeter to say if it was 29.92 inches, we know that's standard atmosphere, 29.92 inches of mercury. But if, say, today we have good weather, we have higher pressure, he will say, well, set your altimeter to 21.98, say, or 30.1. And you will move that little switch there to 30.1, and that calibrates the reading of altitude so that, when you're approaching to land, you have a reading which corresponds to the actual reading at that airport, because obviously you don't want to make that mistake when you're close to an airport. If you're going cross country, say, and you're flying between two faraway places, then during the cross country, everybody sets their altimeter to 29.92. So all the planes have the same reading, regardless of the atmospheric pressure. And if you know that the other plane is reading a certain altitude and I'm reading another one, we're not going to collide because we are actually calibrated to the same pressure. So you see, this is a very useful application. Any comments? No? Okay. So, no comments? Okay. I thought that was a neat little story, side story here. Okay, finally, some other more modern pressure transducers that you may encounter. Well, a pressure transducer, when you use the word transducer, it really indicates that we are sort of changing one form of measurement to another. So really, here we want to take a pressure measurement and turn it to an electronic reading. So you can have some form of little electronic circuit that you can connect to your computer, for example, and have a time record of the changes in pressure for whatever reason. You may want to do that. Or you may have a control device. You may have something that if the pressure goes above a certain point, open the valve. If the pressure goes below a certain point, add more gas or something like that. You could have a control. To be able to have a control loop of that sort, obviously, your pressure measurement, you can't just rely on a column of liquid because that requires a human looking at the column and reading a measurement. This requires an electronic signal. And for an electronic signal, we need to use a transducer. So some of these devices are based, for example, on what's called a piezoelectric material. If you're interested, you can look this up a little bit on your own time. But piezoelectric material basically can generate an electric potential from responding to an applied stress. And so using these piezoelectric materials, you can construct all sorts of little instruments that are much more elaborate and sophisticated than the manometers that we've just described. But for the purposes of the exercises in this course, we'll just work with manometers. Okay? Well, you'll have some examples available to you on Blackboard, and you'll have to also on your homework do some of these problems. Okay, so next class at the ECL lab, so that you can have a computer for a demonstration and some exercises that are going to be related to statics and calculating forces in under pressure.